All right, so this is a program that the Chicago Public Schools introduced. They were very worried that kids were still doing remedial math in 9th grade, and they decided to try to take on this problem head on. Developed a 2-period math sequence in 9th grade, where it was usually the same teacher doing both periods, same students to a large extent. And the first period was more kind of straight up instructional, and the second period was more problem solving and group problem solving. So teachers were fairly well trained. So it was a nice, honest attempt by the Chicago Public Schools to boost math achievement in 9th grade. And the way they decided to roll this out, not everyone in Chicago Public Schools needed a double dose of algebra in 9th grade. So they decided to take the state test, math test in 8th grade, take those scores, and simply divide all the would-be 9th graders who are coming in from 8th grade into 2 groups: those who scored below the median on the 8th grade math test, and those who scored above the median on the 8th grade math test. And I offered double dose to everyone, or as close as the Chicago Public Schools can do, to everyone who was below the median, and did not explicitly offer double dose to anyone who was above. Right? So, with any big rollout, you're going to get some leakage. Some of the people who were offered weren't able to enroll in double dose. Some of the people who were above the cutoff and weren't offered did get double dose. But by and large, as we'll see, that it was a pretty sharp distinction between the fraction of below median math scorers who received double dose versus those who didn't. Okay, so these kids were then tracked in records, school records. So who actually enrolled in double dose, what their grade 9 state test scores were. All the kids took ACT tests in, I think, 10th or maybe 11th grade. So you had both math and verbal scores on that test. What kids went on to take geometry, throughout their high school careers, how many math courses they took. Which kids graduated high school in 4 years, which kids graduated high school in 5 years, and which kids went on to at least enroll in post-secondary education. All right, so in terms of, usually you've got these tiny programs that roll out to a couple hundred kids, and you follow them, maybe to the end of the program, maybe a little bit beyond. But here you've got, thousands and thousands of kids in the entire Chicago Public Schools who were offered this program, and you've got all these administrative data that you can use to track how they do. So that's the setup. And we want to figure out a way to somehow use this assignment scheme below and above the median on 8th grade math test scores to approximate a random assignment of being assigned to double dose. And the trick is, and this is what I talked about in the recorded lecture, is that you've got the 50th, it's actually the 49.5 percentile for math scores, 0, 100. And then you've got various outcomes. In fact, we're double dosed. Math scores, graduation rates, etc. And what you want to do is try to see to what extent these outcomes differ according to the people who got double dose versus those who didn't, right? And what you're using is this relationship between mass scores and all these outcomes to try to infer with this discontinuity at the 50th percentile what the impact of double dose was. And the kind of basic scenario would be, you know, a scatter of points for people below the 50th percentile that leads up to the point when they were allegedly no longer eligible. And then for the people who were above the 50th percentile, well, all of whom by design weren't eligible, but some of them took it up. You really want to see what the difference is. And what this design gives you is an estimate of this difference. This is the impact of double dose. In this case, assignment to double dose on outcomes. Okay, so everyone see the setup? Now, you know, there are all sorts of potential problems, people not taking it up and being assigned to it, or not being assigned to it, taking it up. We talked about that in the context of that behavioral program. You know, another aspect of this is that results pertain to students around the 50th percentile. Of math scores in 8th grade. Right, so you know, it's not as good as random assignment where you've got entire populations being randomly assigned to a treatment group or control group. You're really trying to take advantage of the group that's very close to the cutoff in trying to estimate what this difference is. We know how with regression to estimate these kind of differences, right? You can think of these as two different regression lines separated by a constant. This was part of the last lecture. If you want to allow for, you know, that's just adding a constant, a shift for the double dose people. If you suspect that there are different slopes, so maybe this is a steeper slope and this is a flatter slope, then you want to allow for not only differences in the constant, but also differences in the slope. That's a more fully interactive model. That was part of the last lecture too. So things are pretty straightforward, and they are summarized in this equation. In the article, equation 1, right? The outcome is a function of a dummy variable equaling below the 50th percentile. Plus the 8th grade math score, plus the interaction between the two, right? And this this gives you the equations that will give you an estimate of the double dose effect. So that's one approach. That's the approach that I talked about last time. The approach that they take is a little more sophisticated than that. They estimate two equations. One predicts whether they actually did get a double dose of algebra, right? Knowing whether they're above or below the 50th percentile, it tells you who was likely offered a chance to be in double dose. School records will tell you who actually was double dosed, right? So this is going to be, in their notation, some A low score, below the 50th percentile, plus B math score, plus C interaction between the two. That predicts whether you're in double dose. And then the equation that is most valuable is to have the outcome, math scores, graduation rates, and so forth. With a direct measure of double dose plus controls. So this, and this is kind of the trick, if this is equation 1 and this is equation 2, then this is the predicted probability of being double dosed, in other words, of having these two algebra courses. That we estimate from equation 1. Sometimes you'll put a little hat symbol to indicate a predicted value, right? So we learned the kind of simple way, the somewhat more complicated way, and this is a little bit, we're not going to spend much time on this, but I just wanted to make it clear where this came from in the article. You often see these kind of two-stage regressions where the first stage is getting a prediction of double dose, which is pretty well predicted by whether they were below or above the 50th percentile in 8th grade. You get a prediction of that for everybody. And then you can save these predictions for every individual in the data set. That's a new variable that gets plugged into the second equation. So this is obviously the equation you want. The outcome is actually being in double dose plus controls. So you've got a pretty good prediction here. This is not a 1-0 variable, it's a probability, but it's a probability that's pretty close to 1 for people who had math scores below the 50th percentile, and it's much closer to 0 for the people who had math scores above the 50th percentile. So all of the tables will show these coefficients B1, which is their best estimate of what the effect of being double dosed is. it's kind of like the ITT versus TOT, right? This is akin to the TOT. If you actually participate in double dose, what's the impact of that on all these outcomes that we're interested in? Any questions about that?
Greg, could you talk a little bit about the interpretation of that double dose coefficient? So that would be a 1 unit change, and double dose would be what, a percent, like predicted 1% predicted probability increase or something like that?
Yeah, and it's instead of taking on values of 0 and 1, it ranges between 0 and 1. It's a predicted probability, right? So, a 1 unit change in the predicted probability of being double dose is just like the 1 unit change, in going from being in the control group versus the treatment group. So even though people take on values other than 1 and 0, you still have this nice kind of 1 unit change being in double dose with 100% probability versus being in double dose with a 0% probability. So it's just like you've got this treatment variable, and you can interpret it exactly the same way. It is the causal assumptions that this model are met, the causal impact of double dose on our various outcomes, which is exactly what we want, right? We want to know whether the program worked.
Okay.
We don't want to know whether the offer of the program worked. Go ahead, Vanessa.
Sorry. So could we just then substitute the double dose, so like the first equation into the second equation? But you're saying no, that is different. That they're trying to say not the offer, but whether they took it.
No, that's exactly what we're doing. We're getting this predicted value from the first equation.
Okay.
Right. So this is 1, 0, whether they actually were in double dose. You're getting a prediction of that, mainly by whether their math score was above or below 50th percentile. And then that prediction, which is going to be numbers that are close to 1 and numbers that are close to 0 for most people, that prediction gets plugged in, which you've got for every individual, right? You can take this equation, apply it to every individual, get a predicted value. And then you plug in that prediction in the second stage, which gives you exactly what you want, right? It's a number that ranges between 0 and 1, and it tells you a 1 unit change, which is going from a 0 to 1, even though some people are at 0.2 and 0.8.
Okay.
But if you go all the way from a 0 up to 1, that's the impact of being in double dose on the outcomes.
Okay, so going from like for sure you're not in there to for sure you're there, even though your individual probability might be slightly in between.
Exactly.
Okay.
Exactly. You'd expect people whose probabilities are 0.8 to not score as high on these outcomes as someone whose predicted probability is 1.0. Now, if double dose is important, then the more chance of it is that you got double dose, the better your outcome should be.
Sorry, follow-up question if you don't. Is this
sure. Yeah, no, don't apologize.
Is this maximizing then the effect size? Like maximizing to like if you were in it rather than like using a cutoff point? Or like even looking at the graph, because you're looking at the 50th percentile, like is that where the maximum like effect size you would find versus if you're looking at some other point?
Well, it's really the only, it's all you've got. All you've got is an ability to generalize, so I should back up here. What makes this work, kids are very different one from another. The kids who are scoring at the 5th percentile are very different from the kids who are scoring at the 95th percentile in 8th grade. What makes this work is the assumption that the kids who are at the 49th percentile are very much like the kids who are at the 50th percentile
Got
or
it.
the 51st percentile, right?
Yeah.
And it's that very small difference. The further away you get, 49th and a half versus 50th and 1/2, those kids on average are going to be very, very similar. They just had different math scores by a little bit. And they're going to be a mixture of various kinds of kids, but you're going to have the same kind of balance between the treatment group and control group, the people who were assigned versus those who weren't assigned, the same distribution across those characteristics for the kids who had very, very similar math scores. Once you get further away from the 50th percentile, a lot of other factors get mixed in. Why are some kids at the 25th percentile? Why are some kids at the 75th percentile? So you can't say anything about that with this kind of simple analysis. All you can do is say something about kids who are very close to the cutoff.
Okay.
And one of the tricks, you'd like to be able to say something about what's the effect for the kids down at the 5th percentile or the 25th percentile or the 40th percentile. You'd need a random assignment to do that. You'd want a kid in the 25th percentile who was assigned versus not. But in this case, everyone was assigned to a double dose, right? Mm-hmm. So it's only at this 50th percentile that you've got this kind of quasi-random variation. So the only population that you can generalize to from this quasi-experiment are the kids who are very close to the median in terms of their 8th grade math scores. And you can imagine there's kind of this trade-off. You've got all these observations, but you're really only focusing your analysis on a small sliver of those observations, the ones that are close to the 50th percentile. And the further away that you get, the more worried you are the 45th percentile kids, the same as the 55th percentile kids. The further you are away, the more observations you have, right? So the stronger, more stable the estimates, but you're getting further and further away from the 50th percentile and less sure that you're comparing comparable kids. So there's something called bandwidth in all these articles, right? Where bandwidth is the portion of this 0 to 100 percentile that you end up actually looking at. And in the Cortez et al. Article, they kind of zoom down. They show, full results, but then they zoom down between, I think, the 40th and the 60th percentile. But sometimes they take estimates that are even more narrow than that.
Thank you so much. That was very helpful.
Yeah, so it's to mount a random assignment experiment would be incredibly expensive and ethically rather challenging if you wanted to, for this problem, if you really want to know whether double dose helped the 25th percentile kids, you'd have to randomly assign kids to double dose or not at the 25th percentile. And if you really think that all 25th percentile kids deserve double dose, that's a serious kind of ethical issue. So no random assignment here. It's all kind of occurring just because they set up the program in a way that it could be evaluated. And what made it work is this cutoff. It's the same way with Wong et al. With the pre-K programs. What makes that work is that all 5 of these states had very strict birthday cutoffs for which kids got into pre-K and which kids didn't get into pre-K. Okay, so let's keep going here.
I have one more question, if it's okay.
Sure.
So why would you use a prediction instead of the variable itself? Here, double dose, for example, the prediction instead of using the variable.
It's this, you really want to purge the double dose variable here of selection bias, okay? And whether they actually took up double dose is a function of all sorts of complicated things you don't know about. If you plug in a prediction of double dose, based only on these kind of rules about who should have gotten double dose, then you're purging this prediction of all those selection factors. So that's, this is what instrumental variables is all about. It's this two-stage set of equations where the first stage delivers an exogenous, remember exogenous, measure of interest. In this case, being enrolled in double dose. So, I mean, you could stick in whether they were actually in double dose. That's kind of the standard. You want to know whether a program worked. You see whether kids are in the program. If you don't have random assignment, you just try to make do with the records that you've got. And then you see what the impact of being in double dose on the outcome is. The problem with that, Drew went over this again and again and again in his class. The problem with that is that you could have all sorts of factors determining who is in double dose that might affect your outcome independently. And that's the kind of omitted variable bias you want to avoid. And what this kind of two-stage estimation does is that it avoids selection bias, omitted variable bias, by putting in a variable that is only a function of exogenous, not specific to the individual kind of characteristics, right? People don't have control. I suppose they could have underperformed on their 8th grade math test in order to be in double dose, but that's kind of silly to think about. So whether they, the prediction here is only on the basis of their 8th grade math scores and the rules of the program. It doesn't have anything to do with the individual characteristics. So we've got a predicted value here that has no contamination from individual characteristics. So it should deliver a much more convincing causal estimate than just putting in an observed whether they participated in double dose.
So wasn't in this case our double dose only a function of if they were below 50th percentile and above 50th percentile?
That was the key. That was the key variable, right?
Yeah. So what's the difference if we use that binary of if they were below or above 50th percentile?
That is.
Yeah. So because we are adding another error of prediction to predict double dose, right? From
So it turns out if we look at the graph, the chance of being in double dose, isn't. If you look at the 8th grade math score, it doesn't go from 1, 1, 1, 1, 1, 1, 1, and then drop to 0, right? It kind of, well, I can show you the graph in a second, but you really want, you don't just want a 1 or a 0 here. If you've got information that gives you a better continuous probability of being in double dose. And there's more information in the math percentiles than just 1 or 0. But let me show you the graph, right? But this,
Yeah, I can't imagine what it looks like. That double dose would be continuous, but like our the lowest score wouldn't be continuous. But
well,
so was it the main goal to add a nonlinearity and continuity to it?
it was, all right, so this is a full sample. This is the 8th grade math percentile, and this is whether or not the probability of being in double dose, right? So it's not all up at 101 or 0. It never gets above 0.8, and it starts out well below 0.8, and it starts to fall a bit as you get closer to the 50th percentile, and then it goes down to 0 slowly from about 20% or so. But you know what makes this work is this precipitous drop right at the 50th percentile. So if you know what percentile they're in 8th grade, you have a lot of information on their chance of being in double dose. And that chance of being in double dose, you know, goes from 0.5 up to 0.8 and then comes back down to 0.6 and then drops down to 0. So you want to be able to use all the information that you can to get this predicted probability of being in double dose, which is what they do.
Not fully convinced, but okay, we better move on.
Okay, but let me just ask, you know, this kind of general logic is of we don't want to put in whether they were actually in double dose because that has selection factors, omitted variable bias. So we really want something that doesn't suffer from those problems. And this kind of 2-stage procedure where you get a prediction that's a function of things that are totally outside of someone's control, get that prediction 0, 1, or it goes from 0 to 1, and then you plug that prediction into the 2nd stage. That is used repeatedly, not only in regression discontinuity, but in a lot of other kind of quasi-experimental analyses. And what makes it work is this 1st stage has a lot of bite to it. You really get a lot of prediction from whether they were in double dose based on what their math score was. So you always want to find that you know, outside variable that gets a strong prediction, and regression discontinuity designs usually have that, you know, in one case in terms of math scores, another case in terms of birthday cutoffs.
Yeah, thank you.
Okay, any other questions about that? That's a fairly important point. All right, so let me bring up the screen share again. All right, so we've got a nice sharp discontinuity. So this is going from 0 to 100, right? They do this also zooming into the 40th to 60th percentile, right? I said you really just have random assignment, arguably random assignment near the cutoff. So you really want to know in some detail what it looks like near the cutoff. So this takes it from the 40th percentile to the 60th percentile. So I might just say, you know, these points here, they've got thousands of kids in the sample. And yet we've only got, what, 20 points or so in this graph. And what they do is take all the kids who are in the 40th percentile and get an average fraction double dose for them. repeat it for the 41st percentile, 42nd, 43rd, and so forth. So you get just a small number of points that are reflecting averages of hundreds and maybe thousands of kids, and the same thing down here. So, as a technique for communicating research findings, this it's called binning, putting kids in bins, and then looking at their average on the dependent variable is a very effective way of seeing where the action is. If you look at here's Wong et al. Right, they're looking at a well, in this case, it's whether they're what the test scores are. But if you just look at the scatter here, they don't do any binning, right? This is all the kids, and they have a birthday cutoff. They center the birthday cutoff at 0. These are the kids who, got into the program because they were above the cutoff. These are the kids who didn't get into the program. You get younger and younger kids at the time of the test here, older and older kids at the time of the test. So there's generally a positive relationship. The question is, how much of a jump is there right at this discontinuity? But my point here is that by showing all the points, if all these points were black and the lines weren't there, it'd be really hard to tell whether there was any action at all around the cutoff, right? In contrast, Cortez et al. Have just as messy data, but they present it in a way that is much more. You can much more easily see what's going on around the cutoff, and going all the way from 0 to 100. So as you do your quantitative papers, it's always good to put graphs in. People take so much more information from graphs, but it's especially important for every graph that you have to make the graph as effective in communicating what you want to communicate as possible. And I think this technique of binning the observations, of getting average values for the dependent variable with equally sized groups, in this case leading up to the regression discontinuity and afterwards, it's just a very effective way of conveying what's going on. But as you can see, near the cutoff, the fraction double dose goes from about 0.2 to about 0.6. So, on balance, you only have about 0.4 in terms of a kind of a sharp participation difference. And that's the predicted probability that you're going to take into the to the next stage. So if you look, let me okay, so here's the regression version of this. So there are subsamples, poor readers and good readers, but let's just look at the top panel here, panel A. So at the threshold, the average value of being double dosed is 0.24. It's kind of averaging together the people near 0 and the people higher. What this is saying is, this is at the threshold just above the 50th percentile. Your chance of being double dosed increases by 0.38 or 38 percentage points, more than doubling what your chance of being in double dose is if you're just below the threshold. So that's the equation version of the graph we just saw. And then you can start looking at these other outcomes, right? In 9th grade, People who are double dosed, on average, took one more math course. You'd hope that's true because they were getting a second math course, but it's good to confirm that. So one big question, kind of a question about the pattern of effects. They were getting another math course, but what course didn't they get, right, in order to accommodate the additional math course? You know, on average, it was 1/7 of course reduction in other core courses. Almost half of it came from not being in music and art courses. Smaller chance of being in vocational ed classes. So they had, you know, the additional math course had to come from somewhere, and you can see where it came from, and you can ask yourself, well, is that a, you know, was it worth boosting their math scores if they couldn't get music and art courses? That's an interesting question. But this tells you, you know, exactly where the action is in terms of the those other courses. One of the questions in thinking about impacts, you know, if you're grouping together people in with test scores below the median, you might worry that if you learn from higher achieving skill peers, that you're taking these classes with peers who have lower test scores than would have been the case had you been in a more general algebra class. And these are scored in percentile units. So not only is the kind of average math percentile of the people in your class 19 percentile points lower, but it's also a bit more homogeneous. The standard deviation of 8th grade math scores is lower. So that gives you a little bit more context as to what was going on in the classroom and in the other courses for the double dose people. If people have questions, please interrupt me. All right, so now we can get to some of the outcomes. So this is the table that answers the question, well, what is the effect of double dose on these education outcomes, at least early on? This is the 9th grade outcomes. So these equations are just this equation, right? There's the predicted value of double dose scaled on a 0 to 1 scale. You've got these various outcomes. And we just are looking at the results of those regressions. So what do you have? You've got freshman algebra grade point average increasing by about 0.5 point on a grade point average scale. You know, here's the mean. The average GPA for freshmen taking algebra at all is 1.5, a very low amount. So you're going 0.43 above that. Only 62% of kids who didn't have double dose passed freshman algebra. That increased to 73%, or 72% rather. You know, not 100%, which would be disappointing. Earned at least a C. That increased from 35% up to 47%. You know, you can see where the action is. A lot more action for kids, relatively speaking, who got at least a B. That went from 14 percentage points, almost doubled. But relatively little change up in the fraction getting an A. Other core GPA subjects for other subjects didn't change very much, insignificantly. They earned almost another math credit, as you'd expect. And they had a little bit more in terms of total credits earned. Right, so you start to get, go ahead.
Sorry to interrupt. Can I ask a clarifying question?
Sure.
So it seems like the Y bar at threshold would be the average of the double dose group, right?
No, of the people who just above the threshold.
Oh, okay.
So the non-double dose group. So the question is, how much better do you do when you go from just not being eligible to being eligible?
Okay. Okay. So then back to the equation on the board, the one that's number 2.
Right.
I'm having trouble applying the table to the equation because it seems like the coefficient is compared against the control group. But then wouldn't that mean that? No, you know what? I'm good. I'm good. I just answered it. I'm good. I was going to ask why the control group is included in the equation if we're comparing it to the comparison group, the double dose or the control group, but that's equation number 1. Equation number 2 is not. Equation number 2 is a probability.
Exactly.
Yeah, okay, no, I just answered it as I was.
No, that's okay. That's okay.
Thank you.
However it gets answered is, I don't care if it's me or you. It's actually better if it's you, so that's good.
Cool, I call that an epiphany.
That's good. All right, keep going here. So this, this is the graphics version of what we just saw. Oops. There we go. All right, algebra grade point average, right? Of course, I mean, as you'd expect, people who scored low in 8th grade are going to, on average, have the lowest algebra grade. That increases up to the median, then it drops down, and then it increases again, right? So when we saw that impact on algebra grade point average, it was the estimate of this gap. That's all it was. But this is the 40th to 60th percentile. So this is narrowing the field of view down to close to the cutoff. And the more linear these two segments are, the more believable they are, and the more they jump down, the bigger the impact. So this paper has endless graphs, but I love every one of them because they convey so much information. Here's, so what about beyond 9th grade? What is the impact, estimated in the way we just described, of participating in double dose? Well, first looking at whether kids dropped out or moved to other schools or into private schools, that not much of a change. You want to make sure your sample's not changing in a systematic way. A little bit more likely, but insignificant, to take geometry. The people who weren't present were less likely, obviously, to show up taking geometry. So, a little, well, you go from a 62%. So if present, let's concentrate on that. 68% of the people present in 10th grade were observed to pass geometry if they were just above the threshold. That increased by 14 percentage points if they had taken double dose the year before. Math credits went up. Total credits earned went up. So you're starting to see impacts beyond 9th grade, which is what you would hope for. What about 3rd and 4th year of high school? They've got all this stuff in records, right? So it turns out there's not much action here, right? In terms of total credits, math credits beyond, we saw more in 10th grade, but not very much afterwards. A lot of positive but insignificant results here. Total credits earned went up from 3.6 on this scale up by 0.6. But by and large, in terms of credits, not that much of a difference. But here's what's interesting. Look at the ACT scores over here, right? This is 11th grade math scores. These are standardized. So the people just above the threshold were about a quarter of a standard deviation below the overall sample average. And the double dose kids scored about a sixth of a standard deviation higher on the math score. But the single most amazing number here is verbal score, right? Why would taking double dose algebra increase your verbal score on the ACT so much?
Well, I didn't read that particular part, but we do know that a lot of the math that we use and that's using ACT is built upon reading. And so you have to be you need to be a good reader to do well in these tests.
Yeah, it could be the fact that they were exposed to more word problems, right, and had more verbal exposure.
Or even the complex syntax of math is, the better you do as far as even like putting sentences together, the more you're able to read actual like math formulas. There's a lot of research in that.
Yeah. So, any other ideas? So that probably played a role. Well, let me keep going. We'll do the full results. All right. So high school graduation, more credits, higher 10 percentage point higher probability of graduating high school within 4 years, 12% within 5 years. And then there's a college, if I remember correctly, enrolled in any college, right? That goes from 0.28, 28% up by 10 percentage points. So, Brian, is that still your story about effects of double dose? Why should these other outcomes be so positive?
So I can keep. So there's two things happening, right? So one is we're running numbers, and then two is the understanding of the database that you have and how this stuff works. So I would say the science supports what I'm saying, to be honest with you. I understand how we're getting these numbers here, but I think the science, there's a large breadth of literature that equates those two together. But keep going.
So I would say another possible avenue is that it helps to overcome the kind of structural barriers that students face in getting through high school. Algebra is kind of a gateway course that if you can get through it, you can stay on track in high school to be able to graduate on time or close to on time. You have a chance to enroll in a post-secondary institution. So, independent, maybe these impacts come from the additional math skills that kids have, the additional verbal skills that they might have had because of greater exposure when they were learning the algebra. But an equally plausible explanation to me is that there are that what double dose does is help overcome the kind of structural barriers that high schools throw up for kids who come in with relatively low levels of math skills, right? If you can't get through 9th grade algebra and have to repeat it in 10th grade, that kind of throws you behind. And a lot of kids don't recover sufficiently to be able to graduate on time. So, you know, that's speculation, but it's interesting to think. I was going to have a breakout session. We don't really have time for that.
How would that be?
To have you,
ACT verbals increase in ACT scores?
I'm sorry, the question is why the verbal increase?
On ACT scores, how would double, so I guess I don't see that. I understand what you're saying. You're saying that that a lot of times algebra is a read them out course, right? But the increase in, I don't see that connection as well as you do. But I get what you're saying, that yes, it is used as a read them out course, but that inference that you're making there, because how does that on the ACT? Yeah, go ahead.
Yeah. No. So part of it may be what they picked up in double dose, but if you're on track, right, then you're taking the regular English classes as well as the regular math courses, right? And you know, I'm just trying to think of explanations that you might be able to test with administrative data. I mean, ultimately, you want to know what the process is here, right? You want kind of a mediational story about why double dose had these impacts on verbal scores and on high school graduation and college attendance and things like that. So, you know, if my speculation would be that if I could take the administrative data and somehow classify kids to on track in 9th through 12th grade, right? That you'd observe a significant impact on being on track, where on track is not only math scores, not only math courses, but you know, the whole range of courses that kids who successfully complete high school on time sequence through. They don't really have that kind of analysis here, but you know, it'd be interesting to do with the data. You always want a mediational story, right? And whether the data are up to telling that mediational story or not is a important question. But that kind of stimulated my thinking after looking at this. But you know, if you think about, you can talk about the Perry Preschool project run by a bunch of researchers, Abecedarian project run by a bunch of researchers. This was an actual program that was rolled out in a very big urban school district and seemed to be quite successful by these kind of measures. It's not a cure-all, right? Graduation rates don't go up to 100%. Not everyone gets A's in their math classes. But for a policy analysis, you know, you can't hope for miracles. What you do want are concrete changes that that move kids ahead of where they would have been otherwise. And this double dose algebra seems to be the ticket. Interestingly, there's another regression discontinuity for Florida, which had, I think in 6th grade or maybe 7th grade, a accelerated math learning, also a regression discontinuity, and it had no long-term effects, right? So it kind of implies a developmental story where, and I think, you know, I think maybe an institutional story where there just aren't the kind of barriers in getting through middle school successfully that there are in getting through high school successfully. All right, I've been rambling on here, but I find this to be a really cool article.
Well,
Any questions?
I did have a question. Like, how is like the optimal I understand that like they cited someone else for choosing their bandwidth here, but how would you choose the optimal bandwidth for some of these? I guess you're trying to do a regression discontinuity. Like, how would you estimate what the optimal bandwidth choice is? I don't know.
It's a great question. You can dive into this big time, into the deep end. We've got courses. There's a guy in economics, Damon Clark, who teaches, actually, well, D. Shu's class talks about this, and then Damon Clark's class talks about all the kind of state-of-the-art statistical techniques for deciding things about bandwidth. Once these things start to kind of take off, then you have all these arcane technical people coming in and wrecking everything. But it's, what people used to do is, and I think what the Wong article does, is try out narrow bandwidths, somewhat bigger bandwidths, right? As I say, you face this trade-off. Let me stop sharing. You face this trade-off between a really narrow bandwidth, which is really nailing down the causal impact very imprecisely, because there aren't many kids, in a very narrow bandwidth. As you expand out, you start getting more heterogeneous, don't really know whether they're comparable, but you get more precise estimates. So I think, let me just take a look. Let me jump to the Wong et al. Article and see if, I seem to recall a table. Let me see, this is further down. Oh yeah, so here's an example. This is one of the states, right? This is a regression discontinuity around a birthday cutoff that's fairly strictly adhered to. And they take a different approach. They do this two-stage estimation in the last column. That's the instrumental variables. Same kind of principle. You predict weather attended based on only information about your birthday, basically. And then you plug in a predicted probability of attending based on that. These other estimates come from variations on the regression lines that we talked about before. We had just linear forms, but they go crazy. They have a linear form. What if you assume this shift, but outside of the cutoff area, it's linear? What if you allow for a quadratic near the cutoff? What if you have a cubic, a cube term in? So you can get more and more sophisticated in terms of the functional form that you fit. But then they've got this bandwidth set of columns, right? So you can do 50 days, you can do 75 days around the cutoff. There's an uncomfortable, for PVT, there's an uncomfortable change. The big standard errors here. These are not standardized coefficients. But something like math, both of these are significant. The coefficients are pretty similar. But here's the trade-off, right? So this is a wider bandwidth should give you a smaller standard error. And it gives you a bigger one. So were I doing this asynchronously, I would pause my video and figure this out. But I don't have time to do that. Let me see if it's true. Yeah, this is more what I expect, right? The standard error goes from 3.8 down to 2.6 when you've got a broader bandwidth, you've got a lot more people in there. Goes from 5.6 down to 3.9, right? So in general, the broader the bandwidth, the more precise the estimate, but the more biased, potentially biased the estimate is, because you're bringing in people that are far away from the cutoff. So, you know, we don't have time to go over this article in much detail, which I think you can, there's a summary toward the end. You can look at this yourself and I think follow it along. We went through the one in sufficient detail that these should be okay. Oops. So the kind of bottom line. So here we have intent to treat and treatment on the treated. Treatment on the treated come from the instrumental variables analysis. But this is, you know, this is kind of the bottom line. These are effect sizes, standardized differences. And you can see, you know, how different they are one state from another. Print awareness has the biggest impacts. You know, it's almost always half a standard deviation. That's pretty big. Math, smaller, but usually significant difference. And then PBVT is even smaller on average. Well, let me see. I guess you get inconsistent effects on the Peabody picture vocabulary test. Mostly positive effects, right, for math. And then down here in the bottom, there's a kind of an average. 0.68 standard deviation impact of pre-K on print awareness, 0.26 and 0.16 for PVT, which is kind of a picture vocabulary test. So, you know, what's important here is if you think about pre-K policy, what you're doing here is you're administering a test in the fall of the kindergarten year for the kids whose birthday cutoffs enable them to get into pre-K. So they've just finished pre-K. And you're comparing those kids to the same test scores in the fall for the kids who are just starting pre-K, right? So they didn't quite make the birthday cutoff. So that difference is going to be what looks like the short run impact of pre-K programs. This regression discontinuity only works for short-term impacts, right? If you try to get, you know, impacts after kindergarten, you'll be comparing all kids who've been treated with pre-K, right? If you go 1 year later. But you know, in my mind, what's really important isn't just the short-term impact, but it's the longer-term impact. And there've been a couple states, well, Boston and Tennessee, where they actually did random assignment for pre-K. It had these kind of impacts at the end of the pre-K program, but they completely faded out by third grade. Right, so that's actually, if you take my economics class, we'll go over some of this, some of these results. But you know, it's very important to know not only the short-term impact, but also the long-term impact. A much longer conversation.